you have to know the sources as well, the sources for our reactants. Okay, so the sources for the reactants, you have to know them. And let me actually pull another slide here. So nitrogen, we get nitrogen from air. Okay, nitrogen constitutes about 80% of air. 80% of the atmospheric air that we have here, it doesn't comprise, it comprises of nitrogen. Oxygen, it's actually lower than the composition for nitrogen. And if you're asked especially if you're doing chemistry, you have to know what process you use to obtain nitrogen from air. One process is you can use fractional distillation. So here you can use fractional distillation. Okay, so this is the separation of this is the separation of a mixture of gases by their boiling points. Okay, this is separation of a mixture of gases by their boiling points. You find fractional distillation in the case of crude oil, where you separate it into various different components. So hydrogen, you get it from a process called cracking of methane. There's actually another way to get hydrogen. We say electrolysis of water. So you can say, instead of saying cracking of methane, you can also say cracking of natural gas. Okay, so natural gas. This is acceptable, especially if you're doing combined science. Okay, so and then the electrolysis of water, we can also obtain hydrogen, but the way the process, the reason we don't use the electrolysis of water, especially in the industry, is that it's very expensive. When you split water and forming hydrogen and oxygen, that process, it really requires a lot of energy. Okay, so that's why we just stick to cracking of nitrogen gas. So from what you have said so far, you're supposed to know nitrogen comes from air through fractional distillation. There are also some mechanical means of obtaining nitrogen from air, but fractional distillation is the most obvious one. Hydrogen, you should know it comes from cracking of natural gas, and you can also say from electrolysis of water if they say two methods, but the main method is cracking of natural gas, especially in the industry, because we are also considering the economics. If you become an industrial engineer, what you realize is that most of the stuff, or even a chemical engineer, most of the stuff, it also has a bearing on cost. So we want to minimize cost as much as possible. Okay, so the conditions for the Haber process, you need this temperature here, so 400 to 450. So you need this temperature here, 400 to 450 degrees Celsius. You also need 200 atmospheres here. This is considered a high temperature. There's a reason for this. And you also need an ion catalyst. Okay, so and also just look up the difference between a catalyst and an enzyme. They basically do the same things, but then they're different somehow. I want you to look up the difference. Okay, and then you put it in the comment section, the difference between a catalyst and an enzyme. Okay, so even here you still remember what you're talking about in the previous slide, that nitrogen and hydrogen, they're mixed in the ratio 1:3 by volume. Okay, you can say by volume, you can say by the number of moles, it's still fine. Okay, and what happens here is you mix nitrogen from air, hydrogen from natural gas here, you feed them, and once you feed them here through these particular conditions, remember our reaction is reversible. So we also have a part of the what would collect here, a part of that would not be our product, our desired product. So those will be hydrogen and nitrogen here in this chamber. When you cool, when you cool, you get ammonia here, it turns to liquid, but then you still have nitrogen and hydrogen. So this nitrogen and hydrogen gases, you also have to feed them back into our industrial process, into the Haber process again, for them to react, and then you keep on collecting, just like that. The ammonia, you'll be getting it as liquid. Okay, so that's essentially it. you from this slide, remember the conditions. So the conditions are the ratio of nitrogen to hydrogen, it's 1:3. And to remember the ratio, you have to know the balanced equation, which we're going to look at just shortly before we finish the video. But essentially, this one, it's your condition 1, nitrogen to hydrogen, the ratio must be this. This one is your condition 2, this one is your condition 3, this one is your condition 4. Okay, these are your sources, and this one I was just explaining where you get nitrogen and why it's easy to get somehow. Okay, so the last part that I want to teach you is you don't have to remember that this is 3 and this is 2, because there's actually a reason why we have those. We call them stoichiometric coefficients. So there's a reason we have these numbers here. We call them stoichiometric coefficients. Let me actually stoichiometric coefficients. Okay, so if you're doing I probably butchered the spelling there, but if you're doing chemistry, then you probably know stoichiometry. So the investigating quantities and all that, these are called stoichiometric coefficients. Okay, we're going to talk about this in some other video for those who are studying chemistry. But essentially, you have nitrogen gas and you have hydrogen gas. These are reacting to form ammonia gas like this. Okay, and now the two main laws in chemistry. There is in physical chemistry rather, because there is also nuclear chemistry, which we don't cover here. Physical chemistry, we are only concerned about the transfer of electrons or the sharing of electrons, but the nucleus, it's not affected in any way. So the two laws that govern is the law of definite proportions. I actually hinted on it a little bit. So the law of definite proportions says that whenever a molecule or formula is formed, it forms in a definite ratio of the reacting atoms. Okay, so the reacting atoms are always present in a definite ratio. So here it's 1:3. You always find it like that. They are definite proportions. Okay, this law it also applies as well with what we call the law of mass conservation. So you might know it as the law of conservation of matter. Matter, it's always mass or matter, they're always conserved. So whenever you're having a process, you start with some certain material, you always have the equivalent coming out of the end. Okay, you can always account for all the matter. There's an asterisk to read this that we're not going to talk about, but essentially these two laws, they combine to give us a balanced reaction. So it means that for our reactants, they also have to be the same mass with our product, okay, or products. In this sense, it's just one product. So you actually have to balance this to make sure that there are a number of hydrogen atoms present on the left hand side, they're equal to the number of hydrogen atoms present on the right hand side. The number of nitrogen atoms present on the left hand side, they're equal to the number of moles present to the right hand side. Okay, so here you have to do it in a bit non-routine way. So the only way that you can really get good at this is if you balance as many equations as you can, because they're non-routine. There's no one way to do it. But essentially here I can say, okay, nitrogen is 2 here, nitrogen is simply 1 here, so I can put a 2 here. That means that I now have 2 nitrogen atoms here to 2 nitrogen atoms here. Yay, this is good. And here this is 6 hydrogen atoms. That's a problem. I have 2 hydrogen atoms here, so in order to balance them, to make them 6 for 6, I have to put 3 here. Okay, so this is where the ratio is coming from essentially, and you have to be tactful about it. Okay, so if you had said, okay, let me first balance the hydrogen atoms, then it would have been difficult, because here you have half, and here you have 3 here. So here you have 2, here you have 3. And if you're really good at math, then you just know that in order for you to create 3 here, you have to say 3/2, because this 2 and multiply by 2 atoms, you get 3 atoms here. This is 3 atoms, and here this is 1. So in order to get 1 here, you have to multiply by half. Okay, but then you have to clear the fractions. So in that way, to clear the fractions, you actually have to multiply throughout by 2. So this one just becomes N2 again. This one just becomes 3H2. Okay, again. And then this becomes, we're multiplying throughout by 2. Okay, so this becomes this. And essentially, if you remember the first method of balancing the equations that we talked about, if your method is kind of janky, then that's good enough. Okay, stick to that. But essentially, this is it. And we're also going to look at the manufacture of nitric acid in a very short video sometime. But this is essentially it. And just to recap, we covered the Haber process. We said that it's a process to manufacture ammonia. Okay, this was a big deal, and we sustained why it was a big deal. We talked about nitrogen fixing, which I told you to somewhat look up so that you can know some of these things. Learning has to be fun. If you know a lot of things, then it becomes fun. Okay, and then we described the properties of ammonia, the physical properties like it's colorless, and also the chemical properties like it's highly corrosive, it's a basic in nature, and you know, the other physical properties that it's pungent, it's got a pungent smell. Okay, and then we talked about the brief history, and then we covered that why Fritz Haber, why the Haber process was kind of you know, controversial, and he ended up winning a Nobel Peace Prize. We covered that, and we covered the reaction. We explained why this reaction is like this. The G stands for gas in all cases, and then here we say that this is a reversible reaction because of the arrows here pointing in the forward direction and the reverse direction. We explained what a reversible reaction is, and also we touched on the conditions for the Haber process. Okay, so this was really productive. If you watched through this far, then you know these we if you watched this far already, then can you please, you know, just like the video, and if you haven't subscribed yet, just subscribe for those new videos that will be coming. So this was really productive for us. Thanks so much for watching, and thanks so much for supporting. Our channel is growing. So cheers, Yuba out.